Greetings, dear traveler of the cosmos, and welcome to The Sleepy Scientist. I'm thrilled you're here, whether it's under the soft glow of dawn or the quiet hush of midnight, wherever you are in this vast world. Tell me, where are you nestled right now? Is it a cozy bed, a warm blanket cocoon, or perhaps a quiet corner where your cat plots its nocturnal adventures? As we embark on this gentle voyage into the heart of our restless star, the sun, let's pause to share. What time paints your sky? Your support, a gentle tap on the like button or a kind subscription, keeps this starry haven aglow. Tonight, we'll drift through the sun's ceaseless fire, where tiny particles fuse into light that warms our days. So settle in, let your breath soften, and let's wander together into the glowing wonders of the universe, ever awake, ever alive. As we settle into the gentle embrace of this cosmic tale, let's journey back to a time before time, some 4.6 billion years ago, when the universe was a quieter place. Picture a vast, drifting cloud of gas and dust, a humble wisp of creation floating in the endless dark. It wasn't much to look at, mostly hydrogen, laced with whispers of helium and a pinch of heavier elements, all lazing about in the cosmic void. But don't let its simplicity fool you. In the stillness of space, something extraordinary was stirring, a story waiting to unfold. This cloud, part of a grander molecular nebula, was a cradle of star-making ingredients, vast and frigid, yet brimming with potential. And then, as if nudged by the breath of the cosmos, it began to move. Perhaps a shockwave from a nearby supernova, that fiery farewell of a dying star, rippled through the nebula, stirring its sleepy particles into action. Gravity, the universe's tireless matchmaker, took hold, whispering to every atom, every speck of dust, to draw closer, to gather in a delicate dance of collapse. Slowly at first, then with growing urgency, the cloud began to swirl and tighten, like a cosmic whirlpool spinning toward its destiny. As this cloud contracted, its heart grew denser, hotter, more restless. Imagine a crowded room, bodies pressed closer and closer, the air growing thick with warmth. At the center of this collapsing mass, temperatures soared, pressure mounted, and something miraculous began to spark. At roughly 15 million degrees Celsius, in a crucible of unimaginable intensity, the first flickers of nuclear fusion ignited, not with a roar or a blaze, but with a quiet, profound alchemy. A star was born. Our sun, unassuming yet radiant, came into being, a beacon in the darkness, its light destined to touch worlds yet unformed. But let's linger here, in the heart of this newborn star, because what happened next is no ordinary fire. The sun isn't a campfire crackling with chemical flames, nor a furnace burning fuel in any earthly sense. No, what powers the sun is far stranger, far more wondrous: nuclear fusion, the universe's grandest act of creation. Unlike fire, which shuffles electrons in a fleeting dance, fusion rewrites the very essence of matter. It takes the lightest of elements, hydrogen, simple, solitary protons, and fuses them together under crushing pressure, forging helium and releasing a torrent of energy in the process. It's as if the universe itself is sculpting light from the raw clay of existence. In the sun's core, where gravity's grip is unrelenting, conditions are anything but gentle. The temperature, a staggering 15 million degrees, strips hydrogen atoms of their electrons, leaving a roiling sea of naked protons and charged particles, a plasma so chaotic it defies imagination. These protons, positively charged and naturally repelled, dart and collide with ferocious energy. Under normal circumstances, their mutual dislike would keep them apart, like magnets pushing against one another. But here, in the sun's molten heart, the pressure is so immense, the collisions so violent, that occasionally, just occasionally, two protons come close enough for the strong nuclear force to intervene. This force, acting only at the tiniest of distances, binds them together, setting the stage for the sun's life-giving magic. This is where the proton-proton chain begins, the delicate yet relentless process that fuels our star. Picture it, two protons slam together, and through a quirk of quantum wizardry, one transforms into a neutron, releasing a positron, the antimatter twin of an electron, and a neutrino, a ghostly particle that slips through matter like a whisper through a dream. The result is a deuteron, a heavy hydrogen nucleus, fragile but eager. This deuteron quickly finds another proton, fusing to form helium-3, a lighter cousin of helium. And then, in a final flourish, two helium-3 nuclei collide, creating a stable helium-4 nucleus, 2 protons, 2 neutrons, and tossing out 2 spare protons to start the dance anew. Each step releases energy, not in a sudden burst, but as a steady, radiant hum that powers the sun's glow. This energy, born in the core, doesn't rush to freedom. Oh no, it embarks on an epic odyssey, a journey that can take thousands, even millions of years. The sun's interior is a labyrinth of plasma so dense that photons, those tiny packets of light, bounce and scatter, absorbed and re-emitted in a cosmic game of pinball. A single photon might travel mere millimeters before being caught and redirected, zigzagging through the sun's layers for eons before breaking free. When it finally escapes, it races across the void, reaching Earth in just over 8 minutes, a fleeting sprint compared to its long imprisonment. The sunlight that warms your skin today may have begun its journey when ancient creatures roamed the Earth, a relic of a star that never pauses. This fusion, this alchemy, is no easy feat. It demands conditions so extreme, pressures 340 billion times Earth's atmosphere, temperatures that melt the very concept of solid matter, that it's a wonder it happens at all. The sun's core is plasma, the fourth state of matter, a churning soup of charged particles behaving unlike anything we know. Yet from this chaos comes balance. Gravity pulls inward, seeking to collapse the star. Fusion pushes outward, a radiant counterforce. This delicate equilibrium, called hydrostatic equilibrium, holds the sun steady, neither shrinking nor expanding, a glowing orb suspended in cosmic harmony. The sun's mass, 330,000 times that of Earth, ensures this balance endures for billions of years. Too small and fusion would never ignite, too large, and it would burn out in a cosmic blink. Our sun is Goldilocks perfect, a middle-aged star in its main sequence, fusing hydrogen for 4.6 billion years and set to continue for another 4 or 5 billion more. This stability is our blessing, bathing Earth in consistent light, nurturing crops, driving weather, and painting our skies with dawn and dusk. And here's the quiet miracle. Fusion doesn't just light the sun, it forges the elements of life. The carbon in your bones, the oxygen in your breath, the calcium in your teeth, all were born in stars, perhaps not our sun, but its ancient kin. Fusion is the universe's smithy, crafting the building blocks of planets, people, and dreams. As you listen, nestled in your corner of the world, let this sink in. You are stardust, animated by the light of a star that never sleeps, a star whose fire tells the story of creation itself. So breathe deeply, let the wonder settle, and drift with me as we explore further, carried by the gentle glow of the sun's eternal flame. As we drift deeper into the glowing heart of our cosmic tale, let's linger on the wondrous alchemy that powers the sun, nuclear fusion, the silent engine of the stars. It's a process so elegant, so profound, that it feels like a secret whispered by the universe itself. While the sun bathes us in warmth and light, its core is a crucible of unimaginable forces, where the smallest particles dance together to create the energy that sustains life. So, settle into your quiet corner, let your thoughts soften like stardust, and let's unravel the delicate magic of fusion, step by gentle step, as if tracing the path of a photon through the cosmos. Fusion, at its heart, is simplicity dressed in splendor. It's the act of merging atomic nuclei, binding them into something new, something heavier, and releasing a torrent of energy in the process. Unlike fission, which splits atoms apart in Earth's nuclear reactors, fusion is the universe's preferred method of creation. It's how stars shine, how galaxies glow, and how the elements that form you and me came to be. In the Sun, this alchemy begins with hydrogen, the lightest and most abundant element, a single proton orbited by a lone electron. But in the Sun's core, where temperatures soar to 15 million degrees Celsius, electrons are torn away, leaving a roiling plasma, a sea of charged protons and particles, churning in a frenzy of heat and pressure. Imagine this plasma as a cosmic dance floor, where protons zip and collide with reckless abandon. Normally, these positively charged particles repel each other, like magnets pushing apart with stubborn defiance. But in the Sun's core, the conditions are anything but normal. The pressure is staggering, 340 billion times that of Earth's atmosphere at sea level, squeezing protons so tightly that some, against all odds, come close enough to touch. And when they do, a rare and beautiful thing happens. The strong nuclear force, a power that works only at the tiniest distances, snaps them together, overcoming their repulsion. This is the spark of fusion, the moment when the universe rewrites itself. The process that fuels our Sun is called the proton-proton chain, a series of steps as intricate as a celestial waltz. Follow it gently, without rush, as if we're watching the stars align. First, two protons collide with such force that one transforms into a neutron through a quantum sleight of hand, mediated by the weak nuclear force. In this fleeting moment, the proton releases a positron, the antimatter mirror of an electron, and a neutrino, a ghostly particle so shy it slips through matter like a whisper through a dream. What remains is a deuteron, a heavy hydrogen nucleus, one proton and one neutron bound together in a fragile embrace. This deuteron doesn't linger alone. It quickly meets another proton, fusing to form helium-3, a nucleus with two protons and one neutron. A gamma-ray photon, a burst of high-energy light, is born in this union, the first flicker of what will one day become sunlight. But the dance isn't over. Two helium-3 nuclei must now find each other in the crowded plasma, colliding to create a stable helium-4 nucleus, two protons, two neutrons, while tossing out two spare protons like dancers stepping back to join the crowd again. These protons return to the plasma, ready to begin the cycle anew, ensuring the Sun's fire burns on. What makes this process so remarkable is its efficiency and its patience. When four hydrogen nuclei fuse into one helium-4 nucleus, a tiny fraction of their mass, about 0.7%, vanishes, transformed into energy according to Einstein's elegant equation E equals mc squared. That c is the speed of light, a colossal number, and when squared, even the smallest loss of mass becomes a staggering burst of energy. Every second, the Sun converts 620 million tons of hydrogen into helium, losing 4 million tons of mass to energy. Imagine a fleet of 20,000 aircraft carriers dissolving into light every second, and you're still only grazing the scale of it. This energy, in the form of photons, neutrinos, and kinetic motion, radiates outward, fueling the Sun's brilliance. But here's the paradox: fusion is both powerful and slow. The odds of any single proton fusing are vanishingly small. A proton in the Sun's core might wait 10 billion years for its moment to shine. Yet with 10 to the power of 57 protons in the mix, the Sun hums along, producing enough reactions to sustain its glow for billions of years. This patience is our fortune. A faster burning star would blaze brightly but die in mere millions of years, leaving no time for planets like Earth to cradle life. Our Sun, with its measured pace, is a cosmic Goldilocks, neither too swift nor too sluggish, but just right. This energy doesn't leap from the core to your skin in an instant. The gamma-ray photons born in fusion begin a torturous journey, bouncing through the Sun's dense plasma like marbles in a cosmic pinball machine. Absorbed and re-emitted countless times, a single photon might take 10,000 to 1,000,000 years to escape the Sun's interior. By the time it reaches the surface, it's no longer a fierce gamma ray, but a gentler form of light, visible, infrared, or ultraviolet. After eons of wandering, it breaks free, racing across 93 million miles to Earth in just over 8 minutes, painting your world with warmth and color. This fusion isn't just about light, it's about creation. The helium forged in the sun's core is a stepping stone to heavier elements crafted in other stars long gone. The carbon in your breath, the oxygen in your lungs, the iron in your blood, all were born in stellar furnaces, their atoms scattered across the cosmos to form planets, oceans, and you. Fusion is the universe's storyteller, weaving the elements of life from the simplest beginnings. And then there are the neutrinos, those elusive messengers of fusion. Born in the proton-proton chain, they slip out of the sun in seconds, passing through matter, through you, through Earth, with barely a trace. Billions stream through every square centimeter of your body every second, silent witnesses to the sun's inner workings. By studying them, we confirm fusion's quiet pulse, a direct line to the star's heart, unfiltered by the ages it takes photons to arrive. So, as you rest under the sun's gentle glow, consider this. Every ray of light, every breath you take, is tied to this ancient process. Fusion is not just the sun's heartbeat, it's the rhythm of life itself, a slow, steady song that began billions of years ago and sings on, lighting your days, warming your nights, and connecting you to the stars. Let this wonder settle softly, like sunlight on your thoughts, and carry you deeper into the cosmos's embrace. As we drift further into the radiant heart of our star, let's pause to marvel at the sun's hidden architecture, a layered masterpiece that hums with cosmic purpose. From our earthly perch, the sun appears as a simple golden orb, rising and setting with serene predictability. But beneath its glowing veil lies a complex symphony of plasma, pressure, and light. A structure as intricate as a cathedral, yet crafted by the universe's patient hands. So, settle deeper into your quiet nook, let the world fade to a whisper, and join me as we wander through the sun's unseen realms, layer by luminous layer, in a journey that reveals the delicate balance of chaos and order. Imagine the sun not as a single glowing sphere, but as a series of nested realms, each with its own role in the grand ballet of energy. These layers, the core, radiative zone, convective zone, photosphere, chromosphere, and corona, blend into one another, not with sharp edges, but with the fluidity of a cosmic dream. Together, they transform the raw fury of nuclear fusion into the soft sunlight that kisses your skin. Let's begin at the heart, where the sun's story ignites. At the center lies the core, a furnace of unimaginable intensity, spanning just a quarter of the sun's radius, yet holding nearly half its mass. Here, at 15 million degrees Celsius, hydrogen nuclei collide in the proton-proton chain, forging helium and releasing energy in a quiet, relentless pulse. This is the sun's engine room, a plasma crucible where matter is reborn as light. The pressure is staggering, 250 billion times Earth's atmosphere, crushing atoms into a state beyond solid, liquid, or gas. This is plasma, the fourth state of matter, a roiling sea of charged particles, alive with the chaos of creation. Surrounding the core is the radiative zone, a vast region stretching from the core's edge to about 70% of the sun's radius. Here, the energy born in fusion begins its long, wandering journey. Photons, tiny packets of light, emerge from the core as high-energy gamma rays, but their path is anything but direct. The plasma is so dense that a photon travels mere millimeters before being absorbed and re-emitted, scattered in a random direction like a leaf caught in a storm. This cosmic pinball game, called radiative diffusion, can take tens of thousands to 1,000,000 years. Imagine a photon, born when ancient forests grew or mammoths roamed, only now nearing the sun's surface, its energy passed from particle to particle in an endless relay. As we move outward, the plasma thins and the rules of energy transport shift. We enter the convective zone, the sun's churning outer layer, spanning the final 30% of its radius. Here, radiation gives way to convection, the same process that makes soup bubble on the stove. Hot plasma rises in vast bubbles, some as wide as continents, carrying energy toward the surface. As they cool, they sink back, reheated in an endless cycle. These convective cells, visible as granules on the sun's surface, are colossal, each 1,000 kilometers across, shimmering for mere minutes, before dissolving into the sun's restless flow. This is the sun's slow, simmering stew, stirring energy from its depths to its glowing edge. At last, we reach the photosphere, the sun's visible surface, though it's no solid ground. This thin layer, just a few hundred kilometers thick, is where photons finally break free, streaming into space as the light we see. At 5,500 degrees Celsius, it's cool compared to the core, yet hot enough to vaporize any material we know. The photosphere is a canvas of activity marked by sunspots, dark, cooler patches where magnetic fields choke convection. Some sunspots dwarf Earth itself, a reminder of the sun's restless power beneath its serene glow. Above the photosphere lies the chromosphere, a faint, reddish veil visible only during solar eclipses or through specialized telescopes. Here, the temperature mysteriously rises to 20,000 degrees Celsius, defying our expectation that heat should fade with distance. This oddity hints at the sun's hidden dynamics, perhaps shock waves or magnetic ripples, stirring the plasma into a fiery dance. The chromosphere is a fleeting, ethereal layer, a bridge between the sun's surface and its outermost reaches. Finally, we arrive at the corona, the sun's ghostly crown, stretching millions of kilometers into space. Here, the temperature soars to over 1,000,000 degrees Celsius, a puzzle that has baffled scientists for decades. How can the outermost layer be hotter than the photosphere below? The answer may lie in the sun's magnetic field, where twisted loops snap and reconnect, releasing bursts of energy, or in Alfvén waves, rippling through the plasma like cosmic tremors. The corona is sparse, its particles few but fiercely energetic, so it wouldn't burn you, it might even feel cold, despite its heat. This is the source of the solar wind, a stream of charged particles that sweeps through the solar system, painting auroras on Earth and nudging satellites off course. What makes the sun's structure so mesmerizing is its balance. Each layer plays a part in a cosmic relay, passing energy from the core's fusion to the corona's ethereal glow. The core generates, the radiative zone diffuses, the convective zone churns, the photosphere radiates, the chromosphere hums, the corona whispers. Together they form a system both wild and harmonious, held in equilibrium by gravity and pressure. We can't see these layers directly, no telescope can pierce the sun's blinding light, but we glimpse their secrets through helioseismology, studying sound waves rippling through the plasma and neutrino detectors catching the ghostly particles that escape the core. As you rest, perhaps under a blanket or beside a purring cat, consider this. The sunlight that warms your world is the end of a journey that began eons ago, deep within these layers. It's a story of transformation, from the crushing chaos of the core to the delicate glow of dawn. The sun's structure is not just physics, it's poetry, a testament to the universe's ability to weave complexity from simplicity, order from turmoil. Every ray that reaches you carries the history of these layers, a whisper of fusion's fire, a reminder that you are tethered to a star, forever burning, forever giving, in a dance that lights the cosmos and cradles life itself. As we drift deeper into the sun's radiant embrace, let's follow the journey of its most precious gifts, the light that paints our skies and the ghostly neutrinos that slip through the cosmos unnoticed. These are the messengers of the sun's fiery heart, born in the crucible of nuclear fusion, each telling a story of creation, patience, and connection. Imagine yourself nestled in a quiet corner, the world hushed around you as we trace their paths, from the sun's molten core to the earth beneath your feet, and beyond into the vastness of the universe. So, breathe softly, let your thoughts float like stardust, and join me on this gentle voyage through the odyssey of light and neutrinos. In the sun's core, where temperatures soar to 15 million degrees Celsius and pressure crushes matter into plasma, fusion sparks the birth of energy. Each reaction in the proton-proton chain releases gamma-ray photons, fierce packets of light, and neutrinos, those elusive particles that defy the rules of matter. These are the sun's first emissaries, carrying the story of its nuclear fire. But their journeys could not be more different. While neutrinos slip away like whispers, photons embark on an epic, meandering quest, one that can span millennia before reaching your eyes. Let's begin with the photons, those radiant travelers we know as light. Born as high-energy gamma rays in the sun's core, they face a labyrinth of plasma so dense that a single step forward is a triumph. The core is a roiling sea of charged particles, and a photon travels mere millimeters before being absorbed by an atom, only to be re-emitted in a random direction. Picture a weary wanderer in a cosmic fog, stumbling through an endless crowd, redirected at every turn. This process, called radiative diffusion, is no swift escape. A photon might take 10,000 to a million years to navigate the radiative zone, a region stretching from the core to about 70% of the sun's radius. Each collision softens its energy, transforming it from a gamma ray to less ferocious forms, X-rays, ultraviolet, and finally, visible light. As the photon nears the convective zone, the sun's churning outer layer, the journey shifts. Here, vast bubbles of hot plasma rise and fall, carrying energy like a cosmic conveyor belt. The photon, now caught in these currents, rides the waves of convection, inching closer to freedom. At last, it reaches the photosphere, the sun's glowing surface, where the plasma thins enough for light to break free. After eons of wandering, the photon escapes, racing across 93 million miles of space in just over 8 minutes to warm your skin or dance on a leaf. The sunlight you see today may have begun its journey when ancient civilizations carved their first stories into stone, a relic of the sun's patient labor. This journey is a testament to the sun's complexity. The light that feels instantaneous to us is the endpoint of an ancient pilgrimage, a relay through layers of plasma, each photon a survivor of countless collisions. When you bask in the sunrise, you're not just feeling warmth, you're touching a moment born billions of years ago, a spark from the heart of a star that has traveled through time to find you. Now let's turn to the neutrinos, the sun's silent couriers. Unlike photons, neutrinos are born with a kind of cosmic impunity. With almost no mass and no electric charge, they interact so weakly with matter that they slip through the sun's dense plasma as if it were empty space. While a photon struggles for millennia, a neutrino escapes the core in just 2 seconds, streaking toward Earth at nearly the speed of light. Billions of neutrinos pass through every square centimeter of your body every second, unnoticed, untouched, like ghosts gliding through a dream. They carry direct evidence of the sun's fusion, a snapshot of the core's inner workings, unfiltered by the layers that slow light's escape. Catching these neutrinos is no small feat. They pass through Earth itself with ease, ignoring mountains, oceans, and even our most sensitive instruments. Yet, in deep underground laboratories, tucked beneath mountains or buried in mines, scientists have built detectors to capture their fleeting whispers. Places like Super Kamiokande in Japan, a vast tank of ultra-pure water surrounded by light sensors, wait for the rare moment when a neutrino collides with an atom, producing a faint flash of light. These detections confirm the sun's fusion, matching predictions of the proton-proton chain, and offer a window into the star's heart that photons, delayed by their long journey, cannot provide. The contrast between these travelers is poetic. Photons, bold and radiant, fight through the sun's depths, emerging as the light that shapes our days. Sunrises, rainbows, the glow of a child's smile. Neutrinos, shy and intangible, slip away unnoticed, carrying secrets only science can hear. Together they tell the story of the sun's dual nature, a visible giant that lights our world and a hidden furnace whose depths we glimpse through particles that defy capture. This journey of light and neutrinos binds us to the sun in ways both intimate and cosmic. The photons that reach you fuel life itself, driving photosynthesis, warming oceans, and stirring the winds. Every blade of grass, every breath you take, traces back to the sun's fusion-born light. Neutrinos, though invisible, remind us of our place in a universe far larger than ourselves, a realm where particles dance through stars and planets alike, indifferent to the boundaries we imagine. As you rest, perhaps under a starry sky or beside a flickering candle, let this sink in. The sun's gifts are both immediate and eternal. The light that warms you is a survivor of an ancient odyssey, a spark from a star that burns for you. The neutrinos that pass through you are messengers of a process that began before Earth was born, linking you to the cosmos's deep past. Together they weave a story of connection, of energy transformed and shared, of a universe that creates light from chaos and life from stardust. So, let your thoughts drift, carried by the glow of a star that never sleeps, and rest in the quiet wonder of its endless giving. As we linger in the gentle glow of our star's story, let's turn our gaze to the delicate balance that keeps the sun alive, a cosmic dance of forces so perfectly poised it feels like the universe's own heartbeat. This equilibrium, known as hydrostatic balance, is the silent choreography that holds the sun together, neither collapsing under its own weight nor bursting apart in a blaze of excess. It's a harmony that has sustained our star for billions of years and will for billions more, cradling life on Earth with its steady light. So, nestle deeper into your quiet haven, perhaps under a soft blanket or beside a purring companion, and let's drift through the sun's inner workings, where gravity and fusion weave a tapestry of stability and wonder. Picture the sun, a sphere of plasma 1.4 million kilometers wide, containing 99.86% of the solar system's mass, 330,000 times that of Earth. Its sheer bulk is staggering, a gravitational titan that could swallow 1,000,000 Earths and still have room to spare. This mass exerts a relentless inward pull, a cosmic embrace that seeks to crush the sun into a denser, smaller form. Gravity, the universe's sculptor, is tireless, drawing every particle toward the core with a force that shapes stars and galaxies alike. Without opposition, this pressure would collapse the sun into a pinpoint, a black hole or neutron star, extinguishing its light in an instant. But the sun is no passive giant. Deep in its core, nuclear fusion fights back, a radiant counterforce to gravity's grip. Here, where temperatures reach 15 million degrees Celsius and pressures are 340 billion times Earth's atmosphere, hydrogen nuclei fuse into helium, releasing energy in a torrent of gamma rays, neutrinos, and kinetic motion. This energy doesn't merely light the sun, it pushes outward, a fiery rebellion against collapse. The plasma, heated to unimaginable extremes, exerts a pressure that resists gravity's pull, like a spring coiled tight, refusing to yield. This is the essence of hydrostatic equilibrium, a stalemate where gravity's inward tug is perfectly matched by fusion's outward push, holding the sun in a state of serene stability. Imagine this balance as a cosmic tug-of-war played out across every layer of the sun. In the core, fusion generates the energy that fuels this resistance, producing enough pressure to support the weight of the layers above. As we move outward through the radiative zone, where photons shuffle slowly through dense plasma, and into the convective zone, where hot plasma rises and falls in vast loops, this equilibrium persists. Each layer bears the weight of those above it, yet the pressure from below, rooted in the core's fusion, holds firm. Even in the photosphere, where light escapes, and the corona, where temperatures soar to millions of degrees, the balance remains, a delicate interplay that keeps the sun whole. This equilibrium is not static, but dynamic, a living balance that adjusts to the sun's rhythms. The sun's magnetic field, born from the churning plasma, adds complexity, twisting and snapping to create sunspots and solar flares. Yet even these disruptions don't break the equilibrium, they ripple through it like waves on a tranquil sea. The sun's stability is a testament to its mass, neither too small to sustain fusion nor too large to burn out quickly. A star half the sun's mass would glow dimly, too weak to nurture a planet like Earth. A star 10 times larger would blaze for mere millions of years, a cosmic firework rather than a steady beacon. Our sun, a middle-aged G-type star in its main sequence, is exquisitely balanced, burning steadily for 4.6 billion years and set to shine for another 4 or 5 billion. This balance shapes more than the sun itself, it shapes life. The steady output of energy, 3.8 times 10 to the 26th power watts every second, drives Earth's climate, fuels photosynthesis, and powers the cycles of wind and water. Every leaf, every breath, every drop of rain traces back to this equilibrium, a gift of constancy from a star that neither falters nor flares too wildly. The sun's light, born in fusion and tempered by its layered journey, arrives at Earth with just the right intensity to warm our planet without scorching it, a cosmic Goldilocks that makes life possible. Hydrostatic equilibrium is also a window into the sun's future. For now, it burns hydrogen in its core, maintaining this balance with ease. But in 4 to 5 billion years, when the hydrogen runs low, the equilibrium will shift. The core will contract, growing hotter and denser, igniting helium fusion in a new phase as a red giant. The sun will swell, perhaps engulfing Earth, as gravity and fusion renegotiate their truce. Eventually it will shed its outer layers, leaving a white dwarf, a cooling ember held up not by fusion, but by quantum forces, a different kind of equilibrium altogether. This distant future reminds us that even the sun's balance is temporary, a chapter in a cosmic story that spans eons. We glimpse this equilibrium through science's patient tools. Helioseismology, the study of sound waves rippling through the sun's plasma, reveals its inner structure, mapping the density and pressure that sustain this balance. Neutrino detectors, buried deep underground, catch the sun's ghostly messengers, confirming the fusion that powers its stability. These tools let us touch the sun's heart, not with our hands, but with our curiosity, piecing together a picture of a star in perfect poise. As you rest, perhaps gazing at a starlit sky or feeling the warmth of a fading day, let this balance sink into your thoughts. The sun's equilibrium is a quiet miracle, a dance of forces that holds a star together and gifts us life. It's a reminder that stability, even in the cosmos, is not stillness, but harmony, a dynamic interplay of push and pull, creation and restraint. Every ray of sunlight that touches you is a note in this cosmic symphony, a spark from a star that burns in perfect balance, connecting you to the universe's deep rhythm. So let your breath slow, your heart ease, and drift with me, carried by the steady glow of a sun that holds the cosmos in its embrace. As we drift through the sun's radiant tail, let's pause to ponder its grand life cycle, a cosmic journey that stretches across billions of years from birth to a quiet, eternal twilight. The sun, our steadfast beacon, is not eternal in its current form, but a traveler through stages of existence, each phase shaped by the delicate interplay of fusion and gravity. Its story is one of transformation, a star that burns brightly now but will one day evolve into forms both majestic and serene. So, settle into your cozy haven, perhaps with a warm drink or the soft hum of night around you, and let's wander through the sun's past, present, and future, carried by the gentle glow of its cosmic destiny. Our sun's story began 4.6 billion years ago in a nebula's swirling embrace, a vast cloud of gas and dust cradled in the galaxy's arms. A shock wave, perhaps from a nearby supernova, nudged this cloud into collapse, and gravity, the universe's patient sculptor, gathered its fragments into a spinning, condensing orb. As the center grew dense and hot, reaching 15 million degrees Celsius, nuclear fusion ignited, and the sun was born, a star in its main sequence, the long, stable phase where it fuses hydrogen into helium in its core. This is the sun we know today, a middle-aged G-type star, glowing with a steady light that has warmed Earth for eons and will for eons more. In this main sequence, the sun is a model of consistency, burning through 620 million tons of hydrogen every second, converting 4 million tons into energy that radiates as light, heat, and neutrinos. This phase, which began at its birth, will span roughly 10 billion years, half of which has already passed. The sun's mass, 330,000 times that of Earth, ensures this longevity. Too small and it would flicker dimly, unable to sustain life. Too large, and it would blaze fiercely, exhausting its fuel in mere millions of years. Our sun is perfectly poised, a cosmic Goldilocks, delivering just the right energy to nurture Earth's oceans, forests, and skies. But even stars age, and the sun's main sequence is but one chapter.